Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about discrete random variables. The definition of random variables can be a bit confusing or even intimidating when you see it for the first time. Our goal is going to be to provide an overview of discrete random variables that connects that mathematical definition to the way we actually use discrete random variables when we're doing data science in practice. So let's get to it. All right, so we're going to give an overview, which means that you may not understand some of the details. Don't worry, they will be explained in the next videos. Our goal is to model uncertain quantities that can take discrete values. Discrete just means that the number of values are either finite or they're countable. Some examples could include you want to model the number of students that are going to attend the class, or the number of goals that are going to be scored in a soccer game, or the number of earthquakes that are going to occur in San Francisco over a year. All of those quantities are discrete. We represent them as random variables, in particular discrete random variables. Just to clarify notation, there's going to be two types of variables that we're going to be looking at. Some will be deterministic variables, and those we write like this. So just, as usual. Some others will be random variables, and those we're going to be writing always with a squiggly line, which is called a tilde, on top. Okay, so if you see a squiggly line, that means that we have a random variable. Deterministic variables have fixed values. You could replace them by 5 or 73 or some other fixed value. In contrast, random variables represent uncertain values. They could have different possible values, so we have to describe them probabilistically. So we never say the random variable a equals 3. We have to say things like the probability that the random variable a equals 3 is 0.5. We have to describe them using probability. Okay, but what is a random variable? So it turns out that you will get different answers depending on whom you ask. If you ask a data scientist, they will answer the following. Well, it's just an uncertain variable that I put into my model. It's described by probabilities that I have estimated from data. But now let's see what happens if you ask a mathematician. You ask a mathematician, they will tell you, oh, a random variable, it's a function that maps outcomes in a probability space to the real numbers. And this is the definition that I encountered as a student when I first started studying probability. And this was pretty much my reaction. Like, what does this have to do with modeling uncertain quantities? Very confusing. Well, as it turns out, random variables are a bit like cars. Let me explain why. So, the motor of a car is very complicated. I used to live in California. I had a Prius. It would show me on the dashboard kind of like a cartoon diagram of what was going on in the motor. Had no idea what was going on in that diagram. So imagine in a real motor. Have absolutely no idea, no understanding of motors. But that doesn't stop me from driving. All right, you don't need to know about motors to actually drive a car. Instead, you just use the steering wheel and you're fine. In the same way, under the hood, random variables are functions in probability spaces. They have this rather complicated mathematical implementation. But you don't need to worry about this when you're doing data science, because all you need to manipulate random variables is their associated probabilities. Okay, we're going to see what this means in detail in a moment. That doesn't mean that you shouldn't learn a little bit about probability spaces, and I would argue that it's a good thing to learn a little bit about probability spaces, even if you're just going to use random variables to model. But it's also good to know that this is kind of like mathematical implementation that is going to remain under the hood while we are doing probabilistic modeling, so you shouldn't freak out too much about it. Okay, so what's the plan? First, we're going to provide this mathematical definition of random variables. Then we're going to talk about the probability mass function, which encodes all of these probabilities that characterize a random variable. And then we're going to explain how to estimate the probability mass function from data, which can be done in a non-parametric way or in a parametric way. Okay, so let's get to it. The best way to introduce the mathematical definition of random variables is using an example. So imagine that we have a probability space which represents two rolls of a six-sided die. Okay, each outcome can be represented as a two-dimensional vector where this guy is the first roll, which can be 1, 2, 3, 4, 5, or 6, and this guy is the second roll. Okay, so to produce an outcome in this probability space, we roll the die twice. You couldn't see me rolling the die. You roll the die twice, and those two numbers, that vector is the outcome in the probability space. Now what we're really interested in is just the result of the first roll. That's all we care about. And what we realize is that you can actually represent it as a function of the outcome. So this function we call A, okay, maps this outcome, omega, to just its first entry, omega 1. And that's it. This is a random variable. It's a function from the sample space to the real numbers. Realize that this gives you a real number that is 1, 2, 3, 4, 5, or 6. Okay? And now that function somehow represents the outcome of the first roll, if that makes sense. Again, we usually manipulate these functions using their associated probabilities, and these probabilities are encoded in something called the probability mass function. The probability mass function of a random variable A tells us what is the probability that the random variable equals any of its possible values. So in the case of our die, this would tell us what is the probability that the first roll is a 1, a 2, a 3, a 4, or a 5, or a 6. All right? Formally, it tells us what is the probability of the event, of this event, which is all the outcomes that map to that particular to that particular value. So in the case of the roll, the probability at 1 would be all the outcomes that map to 1. So all the vectors whose first entry is 1. Okay, we usually say that the random variable is distributed according to this probability mass function because the probability mass function completely characterizes the behavior of the random variable, as we're going to see in a moment. But first, especially if you're mathematically oriented, you might be asking, how do we know that these probabilities are actually well defined, that the probability measure is going to assign probabilities to these events in the sample space? And that's a very good question. So let me draw a very simple sample space. Here we just have a random variable that can take 3 values. Here I've drawn the values that map to A1. Okay, so you can think of any outcome here will be mapped by the random variable to A1. Any outcome here will be mapped by the random variable. Maybe I should put some, oh, this is a terrible drawing, to A2, and so on. So again, this is a Venn diagram, okay? We see the sample space, that is this square with area 1, and inside we have outcomes, and what the random variable does is it maps these outcomes to different values. Here is the event, or the set of outcomes that map to A1. Here is the set of outcomes that map to A2. Here's the set of outcomes that map to A3. So those are events because they're sets of outcomes. And now, if we look at their probabilities, so we look at what probability the probability measure assigns to them, that's going to be the probability mass function. So since, if you remember in Venn diagrams, the probability is given by the area, this guy is going to be 1/4, 1/4, and 1/2. All right, so that's the picture. So that's why the probability mass function assigns 1/4 to A1, 1/4 to A3, and 1/2 to A2. But the question was, why does the probability measure assign probabilities to these guys? Because remember that when we had a probability space, there was this thing called a collection of events where we choose what events we assign probability to. And as it turns out, this, like for an arbitrary random variable, it's not necessarily the case that the probability measure assigns probability to these events. So we just impose it in the definition. So now we're ready to give you the formal definition of a random variable. A random variable is a function that maps the sample space of a probability space to a discrete set that is finite or countably infinite. And when you consider the events that map to each of the values in this discrete set, okay, we're going to call these events AI, these events have to be in the collection so that the probability that the random variable is equal to its possible values within this discrete set is well defined. Okay? Does this make sense? I'm asking because as a student, this didn't make sense to me at all, but at all. Because I was thinking, okay, look, fine, yes, okay, I get it. It's a function from the sample space to the real values. I see how this defines some probabilities, awesome. But now if I want to use a discrete random variable to model a quantity because I have some data, I have to define a probability space which has a sample space, a collection of events, and a probability measure, and then I have to define a function such that the pre-image of each of these values that I'm interested in is actually has a probability assigned to it by the probability measure. This sounds like a complete mess. This is madness. Well, the thing is that in practice, we never do that. So it's true that that's the mathematical definition of random variables, but we never define them like that when we're actually doing probabilistic modeling. You only define them like that in mathematics, where you usually don't explicitly build these probability spaces. Which might be a little bit weird because that's the way, when you're learning about random variables, especially in probability theory, this is the way they are defined from the beginning. I think it's important to say very early on that that's not the way you're going to actually define them when you're working with them in data science. Instead, what we do is we define them directly through the PMF. It's the PMF that eventually we're going to just estimate from data and use to manipulate the random variables. So here, essentially what's always going to happen is that we're going to estimate this from data and we're going to forget about that. And that's how it's going to work when you're doing data science, when you're doing probabilistic modeling. Why can't we actually do this? Well, as it turns out, and we'll prove this stuff more in detail in the next video, if you're interested in the probability that A is in any set S of these discrete values that it can take, you can just sum the PMF over those values directly. You don't have to refer to the probability measure or the events or the sample space or anything. You can just compute it directly from the PMF, which means that the PMF completely characterizes the behavior of the random variable, so you can completely forget about the probability space. Just like you forget about the motor of your car when you're driving. So in practice, again, when we want to model an uncertain quantity, because we're going to manipulate the random variable just using the PMF, all we need to do is to estimate the PMF from data. The mathematician, if you're mathematically inclined, or if you tell this to a friend of yours who's in the math department, they might be like, sure, but how do we know there's an underlying probability space? This makes me a little bit nervous given the definition. Well, it turns out that you can actually build that probability space starting from the PMF, but we're never going to do that because what's the point? But we'll show this in the next video, but it's not too important because we're never going to actually do that. But the mathematicians can rest assured. Okay, so how do we estimate a PMF from data? We're going to see two main ways, the non-parametric method and the parametric method. This is the non-parametric method. So imagine that you have a discrete quantity that you want to model, you model it as a discrete random variable, and you have some data and you observe that the quantity can take these values. What is a reasonable estimate for the PMF at 1? Maybe pause the video and think about this for a moment. Well, we need to think about what this actually means. By definition, that's the probability that the random variable equals 1. So it's very reasonable to use the empirical probability of 1 as an estimator for this. So here we see 1, 2, 3, 4 ones out of 6. So a reasonable estimate would be 2/3, right? And non-parametric estimators for the PMF of a random variable for the probability mass function are as simple as that. Okay, that's the empirical PMF. If you have a set of data, which can take values in a certain discrete set, which in this case we call A, the empirical probability mass function at each value in A is just the fraction of times that that value is observed. So we're just essentially using empirical probabilities to estimate the empirical PMF, because each of the entries in the PMF at the end of the day is a probability. And remember that in this notation, this is 1 if xi is equal to A and 0 otherwise. So this is just the fraction of times that you see A in your data set divided by n. And this is a function of the values in this discrete set. So you do this for every A, maybe I should have said that, in the discrete set. Let's take a look. As I said at the beginning, this is a non-parametric estimator of the PMF. We're going to talk about parametric estimation in a moment. Let's take a look at an example. Imagine that you want to model the length of the streaks of converted free throws by Kevin Durant. Okay, we have this data, which are 377 streaks from 3,000 free throws shot by Kevin Durant in the NBA. Each streak, by the way, is just the number of consecutive free throws that he makes until he misses. So the data look like that. Here he made 2 free throws and then he missed, 4 free throws and then he missed, 17 free throws and then he missed, and so on. And we want to know what's the probability when he's starting the streak of obtaining streaks of different lengths. If we apply the empirical PMF, let's see what we get. There are 42 streaks of length 2. So how do we compute the value of the PMF at 2? Again, feel free to pause the video and think about it. Well, we divide the number of times we observe that by the total number of streaks. Okay. Here what matters are the streaks, not the free throws. That's important to point out. Okay, so the probability is about 11%. So 11% of the time he makes 2 free throws and then he misses. And this is what the empirical PMF looks like. Look at it for a moment and try to ask yourself, are you satisfied with this estimate for the PMF? The answer is it depends what you want to use it for, right? But it's clear that it's a little bit noisy. What do I mean by noisy? These values, for example, are all 0, but this guy is not 0. And these two are also not 0, and this guy is also not 0. Do we really believe that the value of the PMF here is 0, but here it's not? Is there something special about the number 39 as opposed to 38 or 37? Clearly not, right? So this is just because we have limited data. We don't have that many free throws that we have observed. So the probabilities are not exact. And we already talked quite a bit about this in the video on estimating probabilities from data. A possible solution is to use a parametric model. All right, so what is a parametric model? A parametric model is based on a parametric distribution, which is a PMF with a predefined shape that depends on a very small number of parameters. So then typically they're easy to fit, they're easy to adapt to the data, even if we have very little data, because we only have to estimate a small number of parameters. We're going to see what I mean in just a moment. Here we're going to discuss 4 of the most popular parametric distributions, discrete parametric distributions, but there are many, many more. We're going to talk about Bernoulli. I don't know how to pronounce that, to be honest. Bernoulli maybe. I used to say Bernoulli, I don't know why, and I even wrote it wrong for a while. Binomial, geometric, Poisson. All right, so the Bernoulli distribution is really simple. It's just a binary random variable that can take 2 values, 1 or 0, and its parameter theta just gives us the probability of a 1. So the PMF is equal to theta at 1 and to 1 minus theta at 0. You can use it to model things like a coin flip, where the probability of heads is theta. Now imagine that you have n identical coins, you flip them all, and they all have the same probability of heads theta, and you flip them independently. If you do that, then you will get a binomial. The number of heads that you observe is a binomial random variable with parameters n and theta, and its PMF has the following follows the following expression. At a, it's equal to this binomial coefficient times theta to the a times 1 minus theta n to the minus a. We're going to derive this expression in a following video. this is how a binomial distribution looks like when n is equal to 20 and theta is equal to 0.2. This shape of the PMF only depends on these two parameters. And now we're going to see what happens when we change theta. Change theta, the coin flip is heads more often, so things should shift to the right. This is theta equals to 0.5, theta equals to 0.8. Again, this whole shape is just determined by this parameter theta. That's all we need to estimate from the data, theta and n. What if you flip a coin independently until it lands on heads? And again, the probability of each flip is theta and all the flips are independent. Well, the number of flips that you need to get a head is going to be a geometric random variable with parameter theta, and it's going to have this formula that we're also going to derive in a following video. And again, before I show you how they look like, let me point out, because I'm going to do that in a little bit, that you can actually use this model to represent the free throw streaks from Kevin Durant, as long as you assume that each free throw is independent and the probability of making each free throw is the same. Let's be real from the beginning. Are those assumptions, do they hold? Do you think they can be true? Obviously not. But if you make them, you get the advantage of making them is that you will get a model that just depends on one parameter, and therefore will be easier to fit with limited data. Okay, so this is how a geometric distribution looks like for theta equals to 0.2, 0.5, and 0.8. Why does it say alpha instead of theta? Because as you will see in the video on the geometric distribution, I'm going to basically derive it in two different ways, depending on whether we're applying it to the free throws or to the actual distribution. But here alpha is actually theta. Sorry about that. All right, so now for the last parametric distribution, imagine that you're trying to modeling the number of earthquakes in San Francisco over a year. And you make the following assumptions. You assume that the earthquakes occur independently, and also that if you look at an interval of small length, t, the probability of observing an earthquake in that interval is proportional to t and to a constant rate, which is lambda, which you can interpret as the rate at which earthquakes arrive. Okay, earthquakes per year or earthquakes per second or something like that. If you make this assumption, the number of earthquakes is going to be a Poisson random variable with a parameter lambda that has this expression, which again we will derive in a following video. Poisson random variables are very popular in modeling the arrival of telephone calls, the arrival of emails, particle decay, and many other phenomena like this. This is how the Poisson PMF looks like for lambda equals 10, lambda equals 20, lambda equals 30. Again, the whole shape of the PMF is completely determined by a single parameter. So how do we fit those parameters? We can fit them with limited data, that's great, but how do we actually fit them? What we do is we derive the probability of observing the data that we're actually seeing under the assumption that the parametric model actually holds. We say, okay, if we had a geometric distribution with parameter theta, this would be the probability of the data that we are observing. But that probability is going to depend on theta, and we're going to interpret it as a function of theta because the data are fixed. And what we're going to do is we're going to maximize that probability. So we're going to choose the parameters that make the data as likely as possible. We will explain that, with formulas and so on in a future video, but this is the idea. This is called maximum likelihood estimation. When we apply it to Kevin Durant's data, this is what we obtain. So here we're comparing the non-parametric estimator, which is the empirical PMF, with this parametric model, which is based on a geometric distribution, and you can see that it's much smoother. It just depends on a single parameter. All right, so which of these models are better? How would you compare them? Well, you need to evaluate the models, right? But before that, let's I thought we were going to talk about evaluation now. First, let's talk about the advantages and disadvantages of parametric models against non-parametric models. I already kind of said this, but let's say it very clearly again. Parametric models have the advantage that you can fit them robustly with very little data because you just need to estimate a very small number of parameters. They have this disadvantage, which is that the assumptions that they require are usually wrong, as in the free throw example. On the other hand, non-parametric models are very flexible. They don't require many assumptions. But the problem is that they tend to be quite noisy unless you have a lot of data. And we see this in this free throw example. Okay, so how do we evaluate models? How do we compare in our particular example, for example, the parametric and the non-parametric model? Well, you use held out data. That's what you need to do as a data scientist or as a person with common sense. You know nothing about all this model is optimal because blah, blah, blah. No, you need to use held out test data. And that's what we do here. We have 3,000 more free throws that Kevin Durant shot afterwards. And we can compare the empirical PMF, in this case, our non-parametric estimator, with that test empirical PMF of the following 3,000 free throws. And we see that the noise was indeed noise. So here, like this one is non-zero, but in the test it's 0. This one is non-zero, but in our model it's 0. So this stuff that we thought was probably noise was noise. The root mean squared error between these values, which is just like a measure of how different they are, is around 8 times 10 to the minus 3. All right, so how does the parametric model do? The parametric model does better. Okay, this measure of the error is less, and it avoids the noise. Of course, it's not as flexible, so some of this stuff might not be noise, but and maybe with more data, the non-parametric model would be able to estimate it, and the parametric model would not be able to. But in this particular regime, the parametric model performs better because it's not as noisy as the non-parametric model. You might be wondering, but wait a minute, it's making assumptions that are not true. And that's life. You're always going to design models that are wrong. They need to be useful. And in this case, the parametric model is more useful than the others, probably because the assumptions are wrong, but they're not completely crazy. Let me give you another example. And we're going to explain this example more in detail in the video on the Poisson distribution. No, actually in the video on parametric against non-parametric models, rather. So we have some data that is the number of calls that are arriving at the call center of a bank in Israel. Okay? This is data that is available online. And now we're comparing the parametric model and the non-parametric model for different amounts of data. So these are months that we're putting into the training set. The training set is just the set of data that we're using to fit the non-parametric and parametric models. And what we see is that when we have very little data, the parametric model is much better. Okay? This is the error, so the smaller the error, the better. And as we increase the data, the non-parametric model improves until it overtakes the parametric model and becomes better. And this is something that we often see. If you have a lot of data, it's better to go with a more flexible model. And in this case, the non-parametric model is much more flexible, and it avoids making assumptions that are probably wrong. And that's it. So what have we learned? We have learned about the mathematical definition of random variables, which is very intimidating, but we don't really need that much to do data science. It's good to be aware of it. There's a motor in the car, but when you're driving, you don't have to care too much about it. Then we defined the probability mass functions and saw some of its properties, and that's really what you're going to use when you're manipulating random variables, and that's what you're going to estimate from data. And there's two main ways to estimate that from data. You can either do non-parametric modeling, use the empirical PMF, or you can do parametric modeling and use some predefined parametric distribution. And that's all I got. Thank you very much.